Now we come towards the coefficient of viscosity. In the streamline motion, the viscous forces acting between the two layers depend upon the following factors. So in the streamline motion, the viscous forces between the two layers. So that is directly proportional to the velocity gradient between the layers, that is F is proportional to dV by dz, that is derivative of velocity with respect to z. So if we remove the proportionality, we write a suitable constant. So F is proportional to A into dV by dz, or F is equal to minus neta A into dV by dz, where neta is the coefficient of viscosity. If A into dV by dz is 1, then F is equal to neta. So it is shown here, that is the modulus of F is equal to neta. If A is 1 and dV by dz, that is derivative of velocity with respect to z. Z is the distance between the two layers, is 1. Therefore, the coefficient of viscosity of liquid is equal to the viscous force acting between the two layers of the unit area when the velocity gradient at this layer is unity. The coefficient of viscosity is different for different liquids because the nature of molecules are different. Coefficient of viscosity is 0 for an ideal liquid. The coefficient of viscosity of liquid decreases as the temperature increases. So the coefficient of viscosity, that is, decreases as temperature increases. The unit of coefficient of viscosity is kilogram per meter second, and its common unit is poise. And we find that it is equivalent to 1 gram per centimeter second. So 1 kilogram per meter second is 10 poise. Therefore, 1 poise is the coefficient of viscosity of that liquid in which tangential linear force of one dyne acting between the two layers of area 1 centimeter square maintains a streamline motion with velocity gradient of 1 centimeter per second per centimeter. Dimensions of the coefficient of viscosity can be deduced from the formula, that is neta is equal to F over A into dV by dz. So we compute the dimensional equation of F, A, and then dV. So we find that the net dimensions will be M1, L minus 1, T minus 1. Critical velocity and Reynolds number. So when we use the term critical velocity and the Reynolds number, this number decides whether the flow is laminar, stable, or turbulent. If the average velocity of liquid is less than the definite velocity, the motion becomes turbulent. So average velocity of liquid is less than the definite velocity, the motion of the liquid becomes turbulent. The limiting value of this velocity is called the critical velocity of that liquid. Limiting value. So we limit the value of velocity. We change the speed and we come to the limiting value. And that limiting value is called the critical velocity of the liquid. Reynold proved from experiments that there is a relation among the density of liquid, viscosity of liquid, neta, that is, we are referring to coefficient of viscosity, radius r of the tube in which liquid is flowing, and critical velocity Vc. So the relation given as Vc is equal to r neta over rho r, or r is equal to rho Vc r over n. R is called the Reynolds number. This Reynolds number decides about the flow of water. For a fine tube, the value of Reynolds number is 1000. In general, it is called a stable flow. If the velocity of liquid is such that R becomes greater than 2000 approaching 3000, then flow becomes turbulent. And from 1000 to 2000, it remains laminar flow. When mean velocity of the liquid is less than the critical velocity, the flow of the liquid is mainly governed by the viscosity of the liquid, and there is no effect of density of the liquid on it. So density of liquid is not interfering the viscosity of liquid. Now the next point, which is quite important, is when the mean velocity of the liquid is greater than the critical velocity, the flow is mainly governed by the density and the effect of the viscosity is negligible. On eruption of volcanoes, the lava coming out of it flows speedily in the spite of being very thick. Thick means having large viscosity. Its explanation is based on the above facts that is given in point number 5. Well, so now we continue with the principle of continuity. So what exactly we mean by the principle of continuity? It will be clear from this context. We consider incompressible and non-viscous liquid. However, practically it is not possible because every liquid can be compressible to a certain limit and non-viscous not possible, viscous because the property of liquid is to be viscous. So here it is our assumption that if an incompressible and non-viscous liquid flow in streamline motion, that is whose Reynolds number is less than or equal to 1000 through a tube of non-uniform cross section and the velocity of the flow is constant at every point of the tube, then it is called principle of continuity. So what is the principle of continuity? The velocity of flow is constant at every point. That is what the meaning of principle of continuity. From the principle of continuity, A1 V1 must be equal to A2 V2 and AV remains constant. So it is shown here, there is a cross-sectional area. For a bigger portion is A1, for the smaller portion it is A2. When the bigger portion liquid is flowing, velocity will be less, but when the water is flowing in a portion of less area, we find that its velocity will become more. So if we take the product of the A1 V1, that will remain always constant. The velocity of liquid is smaller in the wider parts of the tube and larger in the narrower parts. It is seen in the previous diagram. Energy of the flowing liquid. When we speak energy, how much work can be done by the flowing liquid, and work done is force into displacement. There are 3 types of energies in the flowing liquid. Number 1 is the pressure energy, number 2 is the kinetic energy, and number 3 is the potential energy. So there are 3 types of energies in the flowing liquid: pressure energy, kinetic energy, and potential energy. Now what exactly we mean by pressure energy? Our assumption is P is the pressure, A is the area, and L is the distance. Due to this pressure, then pressure energy of liquid is work done, that is equal to force into distance. For force, we have put the value pressure into area, that is multiplied by distance. So it is PAL. The pressure energy per unit volume of liquid that is given as follows. That is P is equal to PAL over A into L. Well, L will cancel off, A will also cancel off, and we will find that pressure energy per unit volume will be equal to P. Now, how to define the kinetic energy? If liquid of mass m and volume V is flowing with velocity V, the kinetic energy of the liquid will be half mv square. That is, kinetic energy per unit volume of the liquid will be half mv square over volume, or it is half mv square divided by twice the volume. That is equal to half rho into V square, because m over V is rho, that is the density, where rho is the density of the liquid. Now we come towards potential energy. If the liquid of mass m is at height h from the reference level, then the potential energy of the liquid is mgh, where m is the mass, g is acceleration due to gravity, and weight is mg, and mg is force, so force is vector. So it is mgh or F into h. Potential energy per unit volume, that is mgh divided by volume, and it comes to be like m over v is density, so rho gh is the net result.